Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at Adelaide Uni, and this video is about how to get Excel to do a two-way ANOVA and to set up your data correctly to do that and to get the information you need out of it to make a graph as well. Okay. So here's some data, and this is very common how people set it up in Excel, but it's not very useful for doing the data analysis we need to do. But I'll just explain it. This is some pretend data with some plants. We've measured the plant height in two different conditions, dry and wet, and we've measured it with three different concentrations of a particular chemical in the soil, none, low, and high. And we've got 8 plants in all 6 of these combinations, and we measure the heights of all of them, and here they all are. Now this is a two-way ANOVA situation, and it's a two-way ANOVA situation specifically because we have two different ways to affect the outcome. We have the dry versus wet, the condition, and we have the concentration of the chemical, none, low, and high. And the none, low, and high are 3 options for one idea, the dry and wet are 2 options for another idea, and those 2 ideas are affecting the outcome. Possibly, that's what the two-way ANOVA is for, to decide if that is actually affecting the outcome. Now Excel can't do a two-way ANOVA with the data set up this way. It has to have one of those 2 variables as the column labels and one of those 2 variables as row labels. And so I'm going to have to rearrange my data so that it looks the way it needs to look. So I'm just going to move these ones over here. And so these first 8 were the dry ones, and these next 8 were the wet ones. And I'm going to have to remove all of this. So this is how Excel would prefer the data to be set up. If you know you're going to do a two-way ANOVA in advance, and you know you're going to use Excel to analyze the data, then it's probably best to enter it in this format in the first place. But anyway, it didn't take too long for me to get it into the right format. And now I can get Excel to do it. Really important to have all these gaps here, to just have the heading for one condition, and then a gap, and then a heading for the next one at the top of the next one. So I'm going to highlight this. I'm going to go up to the Data tab and click on Data Analysis. If you haven't turned that on, you're going to have to go over to File and Options, and you can find the Analysis Toolpack in the add-ons. So we have 2-factor with replication. That's the ANOVA that we want to do. There's all these other things you can do, but this is the one that we want because we have 2 factors affecting the outcome, which is the concentration and the wet or dry condition. And we have replications because in each of those combinations of conditions, you've got multiple plants. Okay, so highlighting it first wasn't the best plan. This is where we want it, where the data is. And there are 8 rows per sample. 8. The alpha 0.05 is the cutoff for our p-value, where we're going to consider our p-value to be significant. And I'm going to put it on the same sheet as this. So I'm going to click an output range. Let's stick it there. Okay, and it thinks for a bit, and then it produces all of this stuff. All right, so what it's giving me in this summary is that for none, low, high, in the dry, it's giving me count, sum, average, variance, and in the wet, it's giving me the same, and then it's giving me the total. So this average 5.5 is of all the dry ones, regardless of whether, sorry, all the none column, whether they're dry or wet. It doesn't do the same for the just dry and wet overall. Well, I guess it does. These are the that's the mean for all of the dries, and that's the mean for all of the wets. So it does give us every mean that we want and every variance that we might want. Down the bottom, this is where the ANOVA is. And what it's doing is it's telling me which of the different things that I can change might affect the outcome. So focus here on the columns. The columns for us were labeled by this none, low, and high. And so that's our concentration. And then the sample is telling us these 8 things here. That's a sample, that's a sample, that's a sample. And those samples are distinguished by the dry and the wet. I'm going to call that condition. And then the interaction is the interaction between those things. So what this is trying to talk about is the condition is saying, does the variation between 2 different plants that have different conditions but otherwise are the same, how much of the variation is caused by being in 2 different conditions, but it's not really caused by how much is it associated with that. And then the concentration is how much of the difference between 2 plants is because they have different concentrations, and the interaction is a little bit extra. What if the effect on the plant height in the different concentrations is different in the different conditions? And so does condition affect the way that concentration affects the result, and vice versa? That's the interaction, and each of those has a p-value to go with it. The F statistics are there to get the computer to figure out that p-value. So these p-values here, that one goes with the condition, and it says it's a very low p-value. So yes, there is a significant effective condition on the plant height. The concentration, yes, there is a significant effective concentration on the plant height because that p-value is low. But no, there is no interaction because that p-value is high. So if you reported it, you would say those exact sentences. There is no strong evidence of an effective condition on plant height. P-value equals this. You put that in brackets. Strong evidence of an effective concentration on plant height, but no evidence of an interaction. And what that means that there's no interaction is that regardless of your condition, the concentration has the same effect on the plant height, and regardless of your concentration, the condition has the same effect on the plant height. And so that's what those p-values are trying to say. Okay, so the problem with ANOVA is it does say that the condition makes a difference and that the concentration makes a difference, but it doesn't say which one makes a difference the most. We don't know which category within the concentration makes the most difference, and maybe 2 of those concentrations are the same and the third one is different, or maybe they're all different, or whatever. And so we have to find out which one is different to which. And Tukey's honestly significant difference procedure helps us to decide that. Before I do that, it's going to be important for me to find all of the means for all of these 6 groups. I've got 6 groups. I know there's 6 because it's dry with none, low, high, and wet with none, low, high, and that's 6 groups total. I need all of those means, and it will be easier for me to do what I want to do if I put all of those means together in one place. So here we go. So here are my none, low, high means. Now it's going to be easier for me to put them as a column, so that's what I'm going to do. I'm going to paste transpose, and that will put them as a column. So that was none, low, high, and these all ones went with dry. And we have none, low, high again. I'll copy that, paste that, and we want these ones. So I'm pressing Control C here, then right clicking, and it says paste that. Okay, so this is the mean height, and this was the concentration, and this was okay. Let me show you something. If I highlight all of this and I go to insert column graph, it will draw this. And see the labels on the bottom there? It's automatically, because of the gaps between the dry and the wet, said all three of those belong to the dry and all three of those belong to the wet. So this is a kind of graph that you can draw. There are other ways to get this graph to draw what you want. And if you wanted to, you could click on each of these bars and change them to different colors. So for example, if I click on that, go here to format and say format selection, I can change this to have a different color fill like that. I'm going to go Control Y, or on an Apple that would be Command Y, and repeat that same thing. And now I've got the dry ones as yellow and the wet ones as blue. That seems reasonable to me as a color choice. Okay, so that's something that we can do, and we can see that in both the dry and the wet, the low ones have a higher column compared to the other two, and the lowest one is the high column actually. And similarly, we can see that all of the wet ones are sort of generally higher than all of the dry ones. And so that's corresponding to what it's telling me, is that the dry versus wet, there is a difference, but it's a similar difference no matter which of the none low high you're in. Okay. Well, while I'm at it with this graph, it might be really useful to have the standard errors in the error bars on that graph. And so standard error is calculated from the standard deviation, and standard deviation you can get from the variance. So if I copy these variances, here, the standard deviation would be equal to the square root of the variance. And the standard error, which is a measure of how variable all the different means that could have been in an experiment like this are, is the standard deviation divided by the square root of the sample size, which in our case is 8 per group. So those standard errors I could use for error bars. So if I click on my graph and go up here to add chart element and add error bars, I don't want standard error because the computer doesn't really know what standard error is. I'm going to go to the more error bars options and click on custom. And so the up value is going to be the standard error, and the down value is also going to be the standard error. And there's my standard errors on my graph there. They're not very big, that's fine. It does happen sometimes. It's kind of nice if your standard errors are small. Okay, so now I've got error bars on all of my bars. That's lovely. So the next thing to do is, I'm going to do two things at the same time here. It's tradition to put letters on these bars to say which category mean is different to which category mean. And to do that, we need to do some statistical procedures, and we're going to do Tukey's honestly significant difference test. And to do that, we're going to have to calculate the honestly significant difference. So Tukey's honestly significant difference is calculated from a statistic called Q, and from the standard deviation, actually this mean square error here, from this last row in the ANOVA table. And it's also calculated from this thing called the degrees of freedom that's just there, that goes in the within bit in the error table. And it's also calculated from the number of means that you are comparing. So K is the number of means we're comparing, and there's 6 of those means. I mean, we're not really comparing means, we're comparing just the relationship between 6 different options, but we are going to compare the means to do it. So there are 6 means, and the degrees of freedom is this degrees of freedom down here in the within row in the ANOVA table. So that's number 42. And that's the total amount of data minus the number of different means. So we had 6 lots of 8, which is 48, minus the 6 is 42. We're also going to need this MS here. And that is equal to this number. Okay. And we're going to need the number of things per sample, which is 8 for us. All of those numbers together are going to be needed. And along with those numbers, the K and the DF are going to need to calculate a critical value of Q. Critical value of Q. Now, there are tables you can look up to find the critical value of 2. You'll look up the K and the DF and you'll line them up in a table and find a spot for that. I have found a website that does it for you. So just give me a moment. This is the Social Science Statistics website. I'll cut and paste this into the Excel sheet, that web address for you. Okay, and we had 6 means and we had 42 degrees of freedom. Calculate the Q critical. For the 0.05 level, that'll be 4.22. So that's the number I'm going to use. .22 from the website. So if you want to do your Tukey's AHD honestly significant difference, it is the Q number that we calculated times the square root of this MS within divided by the N. And so it's 0.787094. Okay. So that difference, that's how far apart 2 means have to be in order for us to consider them significantly different. And so it's going to be much easier for me to do the job I want to do if I reorder this data. So that I don't mess up the other stuff that I've done, I'm just going to copy this and put it over here. Okay, and I'm going to do something else. I'm going to stick these, I don't have to type them separately, I can just fill down, put them all in, and then I'm going to order this. I don't need these anymore, I shouldn't have copied all of them. I'm going to order these by their mean height. So I'm going to go to data, sort, I'm going to sort them by the mean height. Okay, and now dry high is the lowest, and I can see that in the graph, and then dry none is the next highest, and then wet high is the next highest, dry low is the next highest, and then wet none, and then wet low. Okay, so I know that if I go up 0.789094 from here, from the 4.8, then any mean that's within that zone is going to be considered not significantly different from this one. So plus Tukey's honestly significant difference is that plus this number just here. I'm going to put dollar signs in so that when I copy the formula, it doesn't move what that red one is pointing at. Okay, so let's look at this. This 4.8, this 4.812. If I add the honestly significant difference, it gets me to 5.599. And 5.599 is after this one and before this one. So all of these ones here are within the HSD from that smallest one. So they're all considered not significantly different from that one. So I'm going to label them all with an A. Let's look at the next one. 5.94. Well, that gets you all the way up to here. Okay, so that a new one has come into the mix there, and so I'm going to label them all with an extra letter now, like that. Now let's do the next one. Okay, 5.94, well that's only up to here, so I don't need a new letter because I haven't gone any further in my list. Let's put another one. That's 6.16, that still isn't far enough to get all the way to the next one, so I don't need a new letter. And now this one, the 6.62 does include that one there, and so I need to put a new letter to say that those two are the same. And now I've reached the end, I don't need any more new letters. And so these letters here say which clusters of them are considered to be not significantly different. Now, the logic doesn't transfer just because this one is significantly different from this one because they both have don't have a C. Just because this one is not significantly different from this one and this one's not significantly different from this one, it doesn't mean that these two are considered the same. The further apart they are, the more we think they're different. So this lowest one is definitely considered different from both of these ones. Okay, sweet. So what I'm going to do, I've created my letters. What I'm going to do is I'm going to order them again. Let me put a title on that so it's easier to see. I'm going to order them again back in the original order they were. First they were done, it was dry, 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 etc. So first they were done by condition. I'll add a level and do them by concentration. And now these are the same order they were in before. Dry, none, low, high, dry, none, low, high. Okay, so I'm just going to copy that and pop it over here. All right, well, I need to put those letters on my graph. Well, let's have a look at what we can find. Add a chart element. Data labels, that looks good to me. Let's stick them outside on the top. What it's automatically done is it's put the actual mean in that spot, but I don't want it to be the mean that it puts in that spot. So when I go to these label options, this is the color and this is the effects and this is size. So we can change the alignment. Well, actually, that's just how they are inside their box. So this label options, we can, instead of using the values, we can take the values from this list of cells here, which is where the letters were. Ta-da! And now there's a letter on every one to say which one is similar to which one. Which is, I think, kind of cool. And so this graph contains all the information that the two-way ANOVA and the post-hoc Tukey honestly significant difference test produced. I hope that's helpful to you.